All right, AP Stats, we're going to finish 11.1 today with some follow-up analysis. So if our data leads us to a statistically significant result meaning we reject our null hypothesis and we have evidence to say the alternate is true. So if that happens, we can conclude that our variable has a distribution that is different than what is specified. So if we look at the M&M example and we saw that we would reject the null, we would say, hey, we think our distribution of M&M colors is different than what Mars says. So then the question is, well, which color is the one that is most different? Is it because they put no blue in the bag, or is it because they put 100 blue in the bag, right? That's the question we would have. So we do something called the follow-up analysis, which asks us to examine which category has the largest contribution to our chi-squared value, right? Because our chi-squared is the sum of all of our observed minus expected squared all over expected. And so whichever piece of this is the biggest would be the category that has the largest difference than what we would expect. So let's look at an example. In his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Small little editorial, it is a very good book. If you haven't read any of Malcolm Gladwell's stuff, I would highly suggest. I have a lot of his books if you would like to borrow some. Specifically, since January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. The older players often tend to be stronger, bigger, more coordinated. Thus, they get more attention, playing time, coaching, etc., and they have a better chance of being successful. This is what Gladwell argues. To see if this is true, a random sample of 80 NHL players from the 2009-2010 season were selected and their birthdays were recorded. Overall, 32 were in the first quarter of the year. So let's say Q1, 32. Q2, there were 20. Q3, there were 16. And Q4, there were 12. So there were 32 birthdays in the first 3 months of the year, 20 birthdays in the second 3, etc. Does this give us convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? That's our question. Now, of course, what I just wrote down, is our observed. It's what actually has happened. So we're just going to keep that in the back of our heads. All right, where do we begin? We begin with a state. We would like to test the following. We'll say at 5%. Our null hypothesis, well, what's our null hypothesis? Let's go back to the problem and read it again. It says, do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed? That's what we're looking to find evidence for. So our null would be that birthdays of NHL players are evenly distributed throughout the quarters of the year. And of course, our alternate would be basically that same statement, but just are not evenly distributed. So again, I am going to take a shortcut and I'm going to copy it. Birthdays of NHL players are not evenly distributed throughout the quarters of the year. We've got our significance level. We've got our null and our alternate hypothesis. We can move on to our plan. In our plan, we need to list our inference method and check any conditions. So we really only know one test right now. We will use the chi-squared goodness of fit test, assuming our three conditions are true, random, large sample size, and independent. So random, I'm going to go back, double check. It says a random sample of 80 players. All right. Random sample of 80. Large sample size means we need to look at our expected counts. And what we are expecting, if they are evenly distributed throughout the quarters, is that in Q1, there would be 25%. In Q2, there would be 25%. In Q3, there would be 25%. And in Q4, 25%. Oops, I said 4 and I wrote 4. That would mean they're evenly distributed. And how many players did we sample? Well, we sampled 80. But this is going to be the same across the board, right? If we expect these birthdays to be evenly distributed, and we sampled 80 people, we would expect 20 to be in each quarter, and that, of course, is greater than or equal to 5, and so we're good with our large sample size. Last but not least, independence. Our sample size is it less than or equal to 1/10 of our population. 80 means that our population has to be at least 800. Oops, I added another 0. At least 800. And I would say that's reasonable that there are more than 800 NHL players. I actually don't know that, but I don't know anything about hockey. I would assume the team is at least 20 people. I don't know. All right, state plan. We've got our plan. Now we get to do the problem. In our do, we need to calculate our chi-squared value. And of course, as I mentioned in the last video, you should show some of the work for our chi-squared value. We know it's the sum of our observed minus expected squared over expected, but you do not need to do it all. So in Q1, we had 32 birthdays minus the 20 we'd expect squared all over 20 plus, and then I'm just going to do this. I'm going to say plus in ellipses to say, hey, we know that there are more, but I'm not going to do it by hand. How do we do this again? You are going to put your observed in your list 1, your expected in list 2. Then we are going to go to stat tests and chi-squared GOF. Somewhere in here, we do want to write that the degree of freedom is equal to 4 minus 1 is 3. 4 because there are 4 quarters in the year. And when you do that, hopefully, you get a chi-squared value of 11.2. Then we take this chi-squared value and we find a p-value. Or the probability that we get that chi-squared value or more extreme. Greater than 11.2, but because we did this in our goodness of fit test, the calculator already told us what our p-value is. It should be 0.012. All right, we've got our test statistic, we've got our p-value. We can finish up with a conclusion. Our p-value We need to compare it to our significance level. Significance level, 5%. Ooh, our p-value, 0.012 or 1%. Our p-value is less than alpha, so what are we going to do? We reject our null. We have convincing evidence. To say birthdays in the NHL are not evenly distributed throughout the year. Now let's talk about this follow-up analysis, because since we got a statistically significant result, let's look which part of the year is the piece that is most different. Remember, Malcolm Gladwell suggested that he thinks the older players are stronger, more coordinated, get more playing time and more coaching. Thus, those are the ones that are more successful and make it to the NHL. So that your birthday actually has a big impact of whether you're successful in hockey. So let's consider. I, again, am unable to show you the calculator on this laptop, but I took little pictures of my calculator for the goodness of fit test. And the thing that I want to point out is this right here. CNTRB. It stands for contribution. This gives us the specific chi-squared pieces for our 4 values. So notice we have 7.2, we have 0, and then there's a ... here. If you click the over arrow, which is kind of just like on the right side of your calculator, it will scroll over to 0.8 and 3.2. So these are the different contributions from the quarters in the year. What do we notice? The biggest value comes from quarter 1. Those values are the most different from what we would expect to see. And then notice the second highest is quarter 4, which also makes sense. Birthdays at the beginning of the year are taking up more of our space in our set of data. So we come back and we can do, the follow-up analysis that would say quartile 1, Q1, has the greatest contribution to our chi-squared. It was 7.2. That's pretty big. If our chi-squared value was 11 and 7 of those pieces are from Q1. And this supports Gladwell's claim that hockey players born early in the year are more likely to make it to the NHL. So this was a very quick and easy extra step to just say, hey, we notice, looking at the contributions of our values, that Q1, the first quartile, is the biggest difference we saw. That is all for section 11.1. We'll continue with 11.2 when we get back from break. Work on the homework and let me know if you have questions.